Good morning, my dear students. This is our second class. So in our previous class we have seen about Otto cycle and diesel cycle and the problems related to Otto cycle and diesel cycle and the questions from the Otto cycle and diesel cycle. And also in our second class we are going to see about dual cycle and then its performance and the performance of IC engines, and then about basic concepts about the Stirling cycle and Ericsson cycle. Okay. So about now we are going to see about dual cycle and the performance of IC engines. So in case of dual cycle we can see that is it is otherwise called as limited pressure cycle. So this is a thermodynamic cycle which is meant for high speed diesel and auto hotspot ignition engines. So it has a reversible adiabatic compression and as well as the expansion process. So the constant pressure addition and constant volume heat addition and heat rejection process takes place. So in this cycle, so heat is added here at partly at a constant volume and then partly at a constant pressure. Okay, so this is the diagram which represents. This is the diagram which represents this PV and TS diagram which represents this dual cycle. So in this cycle you can see here that is so 1 to 2 adiabatic compression, reversible adiabatic compression or isentropic process, and here it is from 2 to 4 the heat addition takes place. So that is at constant volume and at constant pressure the heat addition takes place, and then once again here that is a reversible adiabatic expansion, that is from 4 to 5, and here heat rejection takes place. So you can see that so the entropy remains constant during 1 to 2 for this adiabatic reversible adiabatic process, and the heat addition, so that is at constant pressure at constant volume and at constant pressure, at constant volume and constant pressure, so the temperature increases drastically. Okay, so here so that is 4 to 5 is the expansion process, and then it reaches its initial position through, that is the heat rejection takes place. So from 5 to 1 through this constant volume process. So here V1 is equal to V5 and V2 is equal to V3. So you have to remember these things in case of working out these problems. So these are the that is total heat supplied is this Q1 is equal to CV into T3 minus T2 plus CP into T4 minus T3. So you can see here, so the heat addition takes place at constant volume as well as constant pressure. So you get this, that is it is the sum of this for 2 to 3 heat addition and 3 to 4 heat addition. So this takes place at constant volume and here it takes place at constant pressure, and the heat rejection takes place from 5 to 1. So Q2 is equal to CV into T5 minus T1. So in earlier cases in Otto and diesel cycle, so we have compression ratio and cutoff ratio, and here one more ratio is added, that is pressure ratio, that is P3 by P2. So compression ratio R is equal to V1 by V2 and cutoff ratio RC is equal to V4 by V3 and pressure ratio is P3 by P2. So you can see the cutoff ratio. So it starts, the heat addition takes place from 0.2 to 0.4. So you can see here that the cutoff ratio, that is V4, it should be like this, V4 by V2, but V2 is equal to V3. So this is V4 by V3, right? So these are the formulas for efficiency. So you have additionally you have this pressure ratio. So in this dual combustion cycle, so you have to remember all these things. So you have to compare Otto, diesel. So efficiency for this dual combustion cycle is, so you can see here it is eta is equal to 1 minus 1 by R whole power gamma minus 1 into Rp, that is a pressure ratio, then Rc whole power gamma minus 1 divided by Rp minus 1 plus Rp into gamma into Rc minus 1. So the addition, so you have in case of Otto cycle, you have only R, that is compression ratio. In case of diesel cycle, you have compression ratio and this cutoff ratio. And in case of this dual combustion cycle, so you have this R, rho as well as this pressure ratio. Okay, so these are the things which are added. So based on this, so you have to compare this dual cycle with this diesel and Otto cycle. So based on this, so sometimes this dual cycle may act as diesel cycle and sometimes it may act as this Otto cycle. So you have to be thorough with this formula. Suppose what happens if Rp is equal to 0? So what is the cycle it changes? So you have to know all these things. Okay, so and you can see all those. So now mean effective pressure. So this is the formula, but it is very difficult to remember this formula anyhow. So our mean effective pressure, we know that mean effective pressure is equal to the ratio between work done and this stroke volume Vs. Okay, so that is V1 minus V2. So you just remember this formula. Based on that you find the work done and then you find the stroke volume and you can easily find the value of this mean effective pressure. Okay. So now, so just you know the concepts of, so this PV and TS diagram of this Stirling cycle, because in GATE exam sometimes you may get questions related to its PV and TS diagram. So if you go for Otto, diesel, dual, then Brayton, then Stirling and Ericsson cycle, so you may get to match the following questions. So in those cases, so you have to know this PV and TS diagram and what are the processes that are involved in this PV and TS diagram. So how many number of isochoric processes are there, how many number of isobaric processes are there, so then how many number of constant temperature process, that is isothermal process, then reversible adiabatic process. So you have to know all these things, where the heat addition takes place, where the heat rejection takes place. So you have to know all this, so you have to compare all this and you have to study. So then only you may able to work out easily work out the statements which are true or not true, and also you may easily work out the statistical data. So you may easily get the answer. So when you go for numerical statistical type questions, so you have to give the answer. So in those cases, so you have to work out the problem. So you should know what are they and how, when the heat addition, when the heat rejection takes place, so when the compression is very high, when the temperature is very high, so everything should be known to you. So then only you can able to easily, so because we may not expect the same questions as that of the previous years. So you have to be thorough with the concepts. So where and when this process occurs should be well known to you. Okay. So now, so you go for this Stirling cycle. So you can see here, so in this Stirling cycle, you have two isothermal process and two constant volume process. Okay, so you can see that there are two isothermal processes. So the temperature remains constant here, and you can see, so 1 and 2. So two isothermal process and two constant volume process. You can see that the volume remains constant at these two conditions. So these two are constant volume process. V is equal to C, V is equal to C. Here it is T is equal to C and T is equal to C. Okay, so isothermal process and constant. So it is similar to that of, same as that of this Carnot cycle. Okay, so right. So now Ericsson cycle. So in case of Ericsson cycle, it consists of two isothermal process. You can see two isothermal process and two constant pressure process. So these two are constant pressure process. That is 2 to 3. You can see here 2 to 3 and 1 to 4. So or 4 to 1. So they are constant. Pressure remains constant. And in case of Stirling cycle, you know these two are constant volume process. That is isochoric process. So there it is V is equal to C. Here P is equal to C. So the diagram may not be similar. That might not be given as similar in the GATE question. But you know how many number of process, how many number of constant pressure and how many number of constant volume, how many number of constant temperature process takes place. Okay, so you should know the cycle. So when the process occurs. So after the end of the one process, so what is the next process should be known to you. because so that is you may get in X and Y. Okay, so you will get different conditions, so but you have to be thorough with the basic concepts. Okay, so process 1 to 2, so all these are known to you. Okay, so 1 to 2, so you can see that it is a reversible isothermal compression process. You can see the temperature remains constant. Okay, like the 2 to 3 is a constant pressure heat addition, and 3 to 4 is reversible expansion, isothermal expansion process. 3 to 4 is isothermal expansion process, and 4 to 1 is constant pressure heat rejection process. So you should know the PV and TS diagram for all this. So the efficiency of the above cycle, so that is eta of this Ericsson cycle is, so that is output efficiency is output by input. So in this you can see that, so this is the output, so QS minus QR, so that is the output. So the output and the input is amount of heat energy, that is amount of heat energy that is added. Okay, so that is QS. Okay, so TH is the respective temperature for this QH. Okay, so the advantage of this Ericsson cycle is it's a small pressure ratio for given ratio of maximum to minimum specific volume with higher mean effective pressure. So Ericsson cycle is applied by gas turbine, so employing a large number of stages with heat exchangers, insulators and repeaters. So where it is employed, so you can see here, so these are some of the applications of this Ericsson cycle. Now we can go for a question. So far we have seen about the dual combustion cycle, and then Stirling cycle and Ericsson cycle. So now you can see here, so Stirling cycle consists of, so how many number of process, so you can see here, so this kind of, you may get these kind of questions. So 2 constant volume, 2 isothermal, 2 constant pressure, 2 isothermal, then 2 constant volume, 2 no adiabatic. So you can easily eliminate these 2, so no adiabatic. And so 2 constant, 2 isothermal process are there. Okay, but in case of Stirling cycle you have 2 constant volume process, you can see that. Okay, so Stirling cycle, it consists of 2 constant volume process and 2 isothermal process. So when you go to the second condition, so you see here the second condition, it is Ericsson cycle. So 2 constant pressure process and 2 isothermal process, it is Ericsson cycle. So the answer is A. So that is 2 constant volume and 2 isothermal process. So you should know all this, each and every statement. So you should eliminate, try to eliminate the wrong answer. Okay, so that is very important in case of these kind of objective questions. Next is, so special cases of dual cycle are Otto cycle, diesel cycle, Atkinson cycle. So what are the correct statements? So 1 and 2, then 1 and 3, then 2 and 3, and 1, 2 and 3. So you can see, now you have to eliminate the wrong answer. So which is so you know that, so in no way this Atkinson cycle is related with this dual cycle. So you can eliminate. So where are the numbers? This 3 comes. You can easily eliminate, but 1 and 2 should be the correct answer, but you should know how this 1 and 2 is right. Okay, so you see here, if a dual cycle, in a dual cycle, if the cutoff ratio is 0, we get Otto cycle. Okay, if you make the cutoff ratio, using that efficiency equation, that cutoff ratio as 0, so then we get the Otto cycle. Similarly, in case of this diesel cycle, if the pressure ratio or the explosion ratio is 0, in case of this dual combustion cycle, we get this diesel cycle. Okay, so that is why I told you the special cases of dual cycle are Otto cycle and diesel cycle. Okay, so you will get the answer. The answer is 1 and 2. Okay, the answer is 1 and 2. So all the other, so initially we have eliminated, but you can make this as right, but sometimes your choice may not be like this, you may have additional choice also. Okay, so in those cases you should try know how to, that means you should know the efficiency equation. So you should know what are the factors which involve in that efficiency equation. whether cutoff ratio is there or explosion ratio is there, pressure ratio, that is pressure ratio is there, the explosion ratio or otherwise pressure ratio is there. So you should know all these things, right? So next is performance of IC engines. So you can see here, so indicated thermal efficiency. So there are different performance parameters. So like indicated thermal efficiency, brake thermal efficiency and all. So you can see about all these things in this performance of these IC engines. So the next is indicated thermal efficiency. So you can see here, so indicated thermal efficiency is the total power developed by the combustion of the fuel in combustion chamber is called as the indicated power. Okay, so this is called as the indicated power. So this efficiency is nothing but the ratio between this indicated power and the amount of energy in the fuel per second. So this indicated power, so this IP, so divided by this MF indicates the mass of the fuel per second into calorific value of the fuel in terms of kilojoule per kilogram. Okay, so indicated indicated thermal efficiency is the ratio between this indicated power and the amount of energy in the fuel per second. Okay. So next is brake thermal efficiency. So it is defined as the ratio between these two, brake power and the amount of this energy of fuel. So that is in the fuel per second. Okay, so that is brake thermal efficiency is the ratio at heat equivalent to the brake power. So heat equivalent to the brake power. So to heat energy is applied to the engine in the fuel. Okay. So this is the formula. So mass of the fuel and this calorific value, so is required for this brake thermal efficiency. And then mechanical efficiency is the ratio between brake power and this indicated power. So here, so you will get questions on, mostly on the question, if you are getting questions on performance, so you will get questions on this indicated power and brake power. Okay, so this brake power, then indicated power is the sum of brake power and frictional power. Okay, so FP refers to this frictional power. So or otherwise frictional power is equal to indicated power minus brake power. So you can take as you like. Okay, but indicated power is the sum of brake power and the frictional power. Then volumetric efficiency. So it is a measure of this measure of the success with which the air supply and thus the charge which is injected into the engine. So it is a very important parameter. So in the because it indicates the breathing capacity of the engine. This volumetric efficiency, which is nothing but the ratio between the volume of free air sucked in. So that is VA, volume of free air sucked in, by this swept volume, that is VS, swept volume of the cylinder. So that is low pressure cylinder. So volumetric efficiency is one of the important term. So based on the capacity of the engine. Okay, because it indicates the breathing capacity of the engine, right? Then relative efficiency. Relative efficiency is the ratio between this actual thermal efficiency and air standard efficiency. Then mean effective pressure. So it is a parameter, so that it is measured by this formula, that is mean effective pressure is given as a PM. So it is IP is nothing but indicated power. Indicated power is equal to PM LANK divided by 60 into 1000. So PM refers to that mean effective pressure in terms of Newton per meter square, or otherwise you can give it in terms of bar, and L is length of the stroke in meter, and A area of the piston in meter square, and N the speed revolutions in a minute, and small n indicates the number of power strokes. So N by 2 for 4 stroke and N for 2 stroke engines. So this K indicates how many number of cylinders are there. Okay, this K indicates, suppose if it is a 2 cylinder, if it is 6 cylinder, this K has to be substituted with respect to the number of cylinders. Then mean piston speed. So that is the product of this length and the speed. So 2 into L into N, and specific fuel consumption. So it is given as the amount of fuel consumed per unit time by power. Power here indicates the brake power. So the unit is kilogram per kilowatt hour. Okay, so you know this kilogram per hour is nothing but the total fuel consumption, and this kilowatt indicates the brake power. Okay, so this total fuel consumption, that is specific fuel consumption, is the ratio between TFC, that is total fuel consumption, and brake power. So this is this will be in kilowatt. Okay, so you will get the unit, so that as kilogram per kilowatt hour. Okay, then air fuel ratio. So it is defined as the ratio between this actual fuel air ratio and the stoichiometric fuel air ratio. So when it is stoichiometric, when the value of this pi is equal to 1, it becomes stoichiometric. When it is less than 1, it becomes lean, and greater than 1, it becomes rich. Okay, the next one is Mos Test. So it is applicable to, Mos Test is applicable to multi-cylinder engines. So generally it is applicable to multi-cylinder engines. So what happens in this, what we are doing in this Mos Test? So we are going to, so in case of this Mos Test, what we are doing? So one cylinder is cut out by short cutting the spark plug or by disconnecting the injector as the case. So in this test, the engine is first run at the required speed and the output is measured. So under these conditions, all the other cylinders, so they are cut out except the required cylinder. The output is measured by keeping the speed constant at its original value. So the difference in the output is a measure of this indicated horsepower of the cutout cylinder. So for each cylinder, the indicated power, IP refers to indicated power, is obtained and it is added together to find the total indicated power of this engine. Okay, so whatever may be, so you are going to find this total IP of the engine. So now we can move on to the problems, so which are related to this Mos Test. So in case of Mos Test, you can see it was conducted on a 4-cylinder 4-stroke engine, and these are the results which are obtained and at a particular speed with a fuel supply of 6 kg per hour. So you have to find the value of the mechanical efficiency of the engine. Okay, so this is the brake power. So this is the brake power with all the cylinders working. So the brake power is 15.6 kilowatt. So for cylinder 1, when it is cut out, it is 11.1. When the cylinder 2 is cut out, 11.03. Then cylinder 3, 10.88, and cylinder 4, it is 10.66. So this is the question is, you have to find the value of this mechanical efficiency. So we know the formula for mechanical efficiency, that is brake power by indicated power. So the total brake power is given to you. So brake power is, the total brake power is, so it is given as 15.6. So for each and every cylinder, so you have to find the value of the indicated power. So indicated power, the produced in cylinder 1, then cylinder 2, cylinder 3, and cylinder 4. So it is a simple calculation, you can easily get through it. So for brake power is given to you, it is 15.6, and for this cylinder 1, it is 11.1. So 15.6 minus 11.1, then 15.6 minus 11.03, 15.6 minus 10.88, 15.6 minus 10.66. So you will get answers for all this, and if you add all this, you will get the total indicated power. So the total indicated power that is developed is 18.73 kilowatt. So that is 4.5, 4.57, 4.72 and 4.94. So if you add all this, so you will get the value of this indicated power. So you will get the indicated power, and already you know the value of brake power. So brake power by indicated power is that is 15.6 by 18.73, that is equal to 0.8328. So the efficiency is 0.83. So this comes under this numerical statistical questions, that is mechanical efficiency of the engine is that is 0.83. Okay, so you have to correct 2 decimals. Okay, next, a hot ideal gas steadily flows through a turbine with inlet and exit temperatures of 1500 Kelvin and 500 Kelvin. So the minimum mass flow rate is given. The minimum mass flow rate in kilogram per second of the hot gas to achieve a power of, so you have to find this minimum mass flow rate. So for power of 12 kilowatt, not megawatt, it is 12 kilowatt. So if you go this, you should know the formula for this. So this power is equal to m dot Cp into del T. So m should be in kilogram per second and Cp in kilojoule per kilogram second, and change in temperature. So this 12 into 10 power 3, that is the power it is given to you, and mass flow rate int 1.2 is the specific heat capacity. So that 1.2 is the specific heat capacity, and the change in temperature, that is 1500 minus 500. So a simple formula. So you will get m dot into 12,000 divided by 1.2 into 1000. So 1200 you get 10 kilogram per second. So this is the answer for this question. So an ideal hot gas. So you use the power formula, that is m dot Cp into del T. So based on the given data, you have to use the formula. So the next question is, the mechanical efficiency of a single cylinder IC engine is 80%, and the frictional power is given to you, it is 20 kilowatt, and the heat released by the fuel is 200 kilowatt. So you have to find the brake thermal efficiency in percentage. So the brake thermal formula for brake thermal efficiency, the brake power by this heat supplied. So that is mf into Cv. Here it is given as 200 kilowatt, right? So you know so you have to go for the given data. So mechanical efficiency is given there, then frictional power is given there. So if you know the value of brake power, you can easily find the value of this brake thermal efficiency, because the amount of heat supplied is given to you. So brake power, you know, indicated power minus frictional power. Brake power is indicated minus frictional power. So from this mechanical efficiency, that is brake power by indicated power. Already we know that this brake power is equal to indicated power minus friction power by indicated power. So this is known to you. So the only unknown will be this indicated power, because this mechanical efficiency is given to you, that is 0.8. So among the three data, so two data are known to you. So the only unknown data is input power. So indicated power. So you can easily find the value of indicated power, substitute here, and you can find the value of brake power. So from that you can easily find this brake thermal efficiency. So next one is, an automobile engine, it consumes fuel at a rate of 22 liter per hour and delivers 55 kilowatt of power. So if fuel has a heating value of 44,000 kilojoule and density of 0.8 gram per centimeter cube, so what is the efficiency of the engine? So you can see here, so what is the efficiency of the engine? Eta. Okay, so efficiency here, that is given as, so power divided by m dot into Cv. So we have given, we know all these formula, that is what is the power, whether power is given to you, yes, power is given to you, it is 55 kilowatt, and m dot mass flow rate. So mass flow rate, so what is the mass flow rate? You have to find from the data, so that is given to you. So that is volume flow rate is given, and density is given to you, that is a meter cube per hour. So this density is kilogram per meter cube. So cancel these two, you will get in terms of kilogram, that is nothing but mass. So multiply these two, so that is a volume flow rate is given to you. So 22 into 10 power 3 into 800, you will get the value of this mass. So you get the value of this mass, and the calorific value is also given to you. So you can easily get the value of this efficiency. So the next one is, so an objective question, so with answers, so with 4 answers, that is for an IC engine, the indicated power is given to you, then brake power is given to you, then brake thermal efficiency is given, and indicated thermal efficiency. So what is the indicated thermal efficiency? So the indicated thermal efficiency comes in the formula mechanical efficiency. So that is mechanical efficiency, you know, brake power by that is indicated power. So if you substitute in case of this efficiencies, so this can be brake thermal efficiency by indicated thermal efficiency. So brake thermal efficiency is given to you, and you have to find this indicated thermal efficiency, and so mechanical efficiency. So what is the value of this mechanical efficiency? It is given as, so whether mechanical efficiency is given to you. So brake power is given. so brake power and this indicated power. So from this you can find the value of this mechanical efficiency. So the brake power is brake thermal efficiency is known to you. So use this relation. So the only unknown will be this indicated thermal efficiency. You can get the value of this indicated thermal efficiency. So here, so you can see that the answer is 31.25. So you will get the exact values. So when these kind of objective questions are there with the statistical data, so even you will get the exact values 31.25. So that shows that your answer is right. So the next one, so for a 4-stroke petrol engine with brake thermal efficiency of 37% and calorific value is 47 megajoule per kilogram and brake power is 78 kilowatt. So you have to find the mass flow rate, so and that should be corrected up to 2 decimals. Okay, so the brake thermal efficiency is given, we know the formula, that is BP by mass of the fuel into calorific value. So brake thermal efficiency is given to you and calorific value is given. So the only thing is you should find the value of the mass of the fuel, that is the unknown. So you can easily find 17.65 kilogram per hour is the mass of the fuel. The next one is the diameter of the bore and stroke length of a single cylinder, that is one cylinder 4-stroke engine is 0.5 meter and 2 meter. The engine is running at 250 rpm. So calculate the stroke volume, so volume rate in meter cube per second. So these are the answers that are given to you. 4 answers are given to you. So you can see that, so you have to find the value of the stroke volume flow rate in meter cube per second. So the cylinder is single cylinder and it is a 4-stroke engine. D is given to you, then L is given to you, and then N is given to you. So use the formula for stroke volume, that is pi by 4 D square, that is area into length. So area is pi by 4 D square and L into the cylinder is single cylinder and it is a 4-stroke engine. So N by 2, so into this 60. So for this conversion of the seconds, so pi by 4 D is given to you into 2 into the length is stroke length is 2 into N speed is given to you 250 divided by 2 into 60. So the answer is 0.8181 meter cube per second. So you can see here, so 0.8181. So you get this value, exact values. Okay, so while you work out the problem, you will get the exact values in this. So the next one is a 4-stroke petrol engine at full load. It delivers 60 kilowatt. It requires 8.5 kilowatt to rotate it without load at the same speed. Its mechanical efficiency at full load, half load and quarter load. So the mechanical efficiency at full load, when the load is, suppose if the load is P, so when it is P, what happens? When it is P by 2, what happens? When it is P by 4, what happens? So this is the question. So there will be 3 options. So you have to find the 3 options. You can see here. So at full load, brake power at full load is 60 kilowatt. Okay. So the frictional power for all the conditions is given to you. It is 8.5 kilowatt. So you have to find the mechanical efficiency. So that is eta mech. So we know that it is BP by IP. So IP is equal to, so BP by IP is BP plus FP. Okay, so first initially the load is, so for the first condition it is 60 kilowatt, it delivers around 60 kilowatt. So 60 divided by 60 plus, for all the conditions it is 8.5. For the second condition it is 30, 60 divided by 2. It is 30 divided by 30 plus 8.5. For the third condition it is 60 divided by 4, that is 15 divided by 15 plus 8.5. So you will get the answer for all this, and it is 87.59, 77.92 and 77.92 and 87 point, sorry, and the next third one is 63.82. So the option is A. The next question is, a 4-stroke and 6-cylinder gas engine with a stroke volume of 2 liter, it develops 30 kilowatt at 510 rpm. The indicated mean effective pressure is given to you. It is 600 kilonewton per meter square, and the average number of times each cylinder misfired. Okay, so average, what is the average number of times that each cylinder misfires? So indicated power. So and indicated power, so you know the formula for indicated power per cylinder. So if the indicated mean effective pressure is given to you, this indicated power will be, so indicated mean effective pressure into this stroke volume into N is the number of cylinders divided by this 60. Okay, this 60 will be equal to, so that it develops how much of power? It develops 30 kilowatt. That is IMEP into Vs into N divided by 60 is equal to 30 into 10 power 3. Okay, so IMEP is known to you. Indicated mean effective pressure is 600 into 10 power 3. So into Vs is stroke volume is with a 2 liter. Okay, so that is around 0.002. So 0.002 into N divided by 60. So that is N is nothing but the actual number of explosion per minute. Here it is actual number of explosion per minute. It is not the number of cylinders. So actual number of explosion per minute. So that is given how much. So you have to find this actual number of explosions per cylinders. This is N. Okay, so now, so IMEP into Vs into N. So N, you can find the value of the unknown. IMEP is known, Vs is known. So N is not known to you. 630. So this is okay. This is a stator. Okay, so now you get the value of N. So it is around 250. So now you have to find the ideal number of explosions. So in order to find this number of misfiring, so it is a 4-stroke engine. Okay, so the speed is given as 510 rpm. So you have to divide that 510 divided by 2. So it is 255. So now if you subtract this 255 and the number of actual explosion, that is 250, the answer is 5. Okay, so you can see, so it is given in this option. So the option is 5. So you should not take this much of time. Simply you should know the formula for this what is that indicated mean effective pressure, where this indicated mean effective pressure is substituted, so at which place, so what is the value of that power, that is indicated power. So everything should be known to you. So you have to use the formula according to the given data. So what are the data that are given to you? So based on that you have to arrive the formula and substitute in this. So so this is nothing but the number of times each cylinder misfired. Okay, so that N. So already we know that it is around 510 rpm. So for a 4-stroke engine it is by 2 divided by 2, N divided by 2. So you will get the value as 255 minus this value is, using the calculations you will get the value of around 250. That is actual number of explosion per minute is 250. When you subtract these two, you will get the value of number of misfiring. So in this problem you can see that air inhalation rate of a diesel cycle is given to you. It is around 300 kg per hour, and the temperature and the pressures are given. So you have to find the value of the volumetric efficiency. You have to find the value of the swept volume. So the volumetric efficiency is given to you. So eta volumetric. So eta volumetric is equal to, so that what is that eta? That is a volume of, so that is the actual volume, so that is delivered, so by this is stroke volume. okay, or this is not stroke, swept volume. So you have to find the value of this swept volume. So this value is given to you, it is around 0.723 is equal to, so VA divided by VS. This is not known, so you have to find this. So how will you find the value of VA? So we know that VA is equal to this MA into R, A into T. Okay, so this pressure, so that for finding this value of VA, so you are getting this M, R, T and P. So are you getting these values? So mass is given to you kilogram per hour, and R, so you know the value of R, and T, temperature is given to you, and then this pressure is also given to you. So you can easily find the value of VA. So you can see that you can easily find the value of VA here. Alright, so temperature, so everything you can find. So VA is equal to MA into RA into T. So this MA is given to you, and RA is 0.287, and plus into temperature 15 plus 273, 288, divided by that pressure is 1.03 bar. So you have to convert that, and this is into 3600 to find the value in seconds. So 0.0668. So this value is now known to you. 0.723 is equal to 0.0668. So the only unknown is Vs. So you can easily find the value of this Vs. So the next one is a 4-stroke petrol engine at full load, it delivers 60 kilowatt. It delivers 60 kilowatt. It requires 8 kilowatt to rotate it without load at the same speed. And the mechanical efficiency at full load is given. And then brake thermal efficiency is given to you. Calorific value is given. Then specific gravity is also given to you. So you have to find the value of indicated thermal efficiency. So you know that mechanical efficiency is the ratio between this brake thermal and indicated thermal efficiency. So mechanical efficiency at full load is given to you, it is 0.885, and the brake thermal efficiency is also given to you, 0.3. So the only unknown will be indicated thermal efficiency. So you can easily find the value of the indicated thermal efficiency. So it is 33.89. 33.89 is the answer for these things. Okay, so these data, so that is specific gravity, and they are superfluous data. Okay, so they are superfluous data. Okay, so the next question. So a two-stroke IC engine has a mean effective pressure of 6 bar, and the speed of the engine is mean effective pressure is given to you, MEP, then speed N is given, then bore dia and stroke length. So these are all given to you. If the mechanical efficiency eta mech is also given, eta mech is, so these are the data that are given to you. So what is the value of this brake power? So BP, we know the formula for this brake power. So brake power, so comes in eta mech, right? Eta mech is equal to this brake power divided by this indicated power. So brake power, so you should know the value of brake power. So mechanical efficiency is given to you, it is around 65%. So the only unknown is indicated power. So based on these data, so MEP, N, D, L, so indicated power is PM, A, L, N, K into N divided by 60. This is the formula. So N is equal to 1, and also K is equal to 1 for the two-stroke single cylinder. So you substitute all the other values. So this mean effective pressure, and so on, that area, then length, then the speed. So if you substitute all those, so you will get divided by 60. If you substitute, you will get the value of this indicated power. So BP, you have to find the value of BP. So BP is equal to, so IP into eta mech. So this is known to you now, and already this is given, mechanical efficiency is given. So you can easily find the value of this brake power. So the next question is, a 50 kilowatt engine has a mechanical efficiency of 80%. If the frictional power is assumed to be constant with load, what will be the mechanical efficiency at 70% of the load? So what are the data that are given to you? A 50 kilowatt engine is given to you. It has a mechanical efficiency and then it acts as constant load. So if it has 70% of load, 70% of load, so what will be the value of eta mech at 70% of the load? Okay, so you can see here, so what will be the value at brake power at 70% of the load? So you have to find mechanical, use the formula, mechanical efficiency formula, that is brake power by eta mech is equal to brake power divided by indicated power. So the brake power is given to you, it is brake power is 50 kilowatt, brake power is given to you. Then what indicated power is not known to you, then mechanical efficiency is given to you. So you can easily find the value of indicated power as brake power by efficiency. So you can easily find this value, and then you can go for this frictional power. So you can find, because this is nothing but indicated power is nothing but the sum of brake power and the friction power. Okay, so you can find the frictional power also. So because you have to use this in the brake in the load which is at 70%. So that is when the mechanical efficiency is at 70%. So for 70%, so load, what is the brake power? So you have to find that is 35 divided by 35 plus frictional power. So you may not able to substitute the same free indicated power here. So for that only you are going to find this frictional power. So substitute in this place, you have to find this frictional power separately. So that is 12.5. So you will get the value as 0.736. 0.736. So this is the answer. So the next one is comparison of efficiencies. So for same compression ratio and heat addition, upon the same compression ratio and heat rejection. So one is auto, dual, diesel. So this, so always, so this is the symbol, it is greater sign. Okay, so auto, dual and diesel. So you have to remember, so use some codes to remember this. So O, do, D. Okay, so if you use this, so you can remove. So for same compression ratio, whatever may be heat addition or heat rejection, so this is the code you are going to use. So that is the code, and you see here the same code is used, and the same code you can use here also for same compression ratio and heat addition. And now you can see here the peak pressure is maximum. So in all these three cases the peak pressure is maximum, and the peak temperature and heat rejection, then heat input and work output. So whatever may be, these conditions are different, but the same has to be once again used. You see here, so D, diesel and dual and auto. So simply you write this diesel, dual and auto. Okay, so the reverse of this, the reverse of the first case, so that is you have same compression ratio, maybe heat rejection or heat addition, efficiency of auto will always be greater than dual, than this diesel. Okay, so this is the symbol, the same symbol you have to adapt. You see here, auto, dual, diesel. Okay, so you can easily remember all this. So these kind of sometimes you have to use some techniques. It is up to the students to use all this, because we may not able to remember all those, because we as mechanical engineering we have a vast syllabus, so it is very difficult to remember all those. So use some codes and you remember all those, please. And the next question. So for which of the following statements concerning air standard cycles are true? So for a given compression ratio and inlet conditions, Otto cycle has higher efficiency than diesel cycle. So now only we have seen this. So this statement is true. Okay, so it lies in one. Okay, right? So but anyhow you see here all the above is there. So you can reject, you can eliminate these two. Easily you can eliminate these two. So now only you have two options. So one is A and the other option is D. Okay, so you go to the next one. So because now it is all the above, so you have to consider other three also. Okay, so for a given maximum cycle pressure and temperature and inlet condition, diesel cycle has higher efficiency than Otto cycle. So for a given maximum cycle pressure and temperature, yes, and inlet conditions. So we have seen this in diesel cycle. So when you go for higher pressures and temperature, and when you change the inlet conditions with respect to its volume, so certainly diesel cycle will have higher efficiency than Otto cycle. We know, so that R, value of R is compression ratio V1 by V2. Here in case of Otto cycle it is only 6 to 10, but in case of diesel cycle the compression ratio is around 14 to 23, around not 14, 12 to 23. You see, these are the based on the inlet conditions. So the value also increases, right? The compression ratio value increases. It is based on the inlet conditions. Am I right or not? V1 and V2. So these are all inlet. This V1 is comes under the inlet condition. So based on this, so this value also increases. So the higher compression ratio, so will leads to this higher efficiency. So this diesel cycle has higher efficiency than Otto cycle. Yes, right. The next one is thermal efficiency of Otto cycle increases with the increase in compression ratio, right? It is right or not? 1 minus 1 by R whole power gamma minus 1. So if you go on increasing the value of R and gamma, so we have seen in the Otto cycle. So if you go on increasing R and gamma, so the value of eta will also increases. But due to practical difficulties, we may not able to increase the value of R and gamma beyond 12 or 10, because we go for that knocking conditions. So in order to avoid that, this value of R, the increase of R and gamma is limited. So the value 3 is also right. And when you go for the fourth one, for a given compression ratio and inlet conditions, the thermal efficiency of diesel cycle increases with cutoff ratio. Okay, increases with cutoff ratio. So at this place, so you have to study the statement thoroughly. Okay, so it decreases. It decreases. So we have seen in diesel cycle, if you add one more bracketed factor, so the efficiency goes down. Okay, so in case of Otto cycle, you have only this. So when you make this into a diesel cycle, the same 1 minus 1 by R whole power gamma minus 1 into 1 by gamma into this rho power gamma minus 1 by rho minus 1. By rho minus 1. So this bracketed factor should always be greater than 1. Okay, so if it is like that, so here you have this gamma and this value reduces, this value increases. So the efficiency will go down. Okay, so the efficiency will never increase. The efficiency of diesel cycle, here it is given as increases with cutoff ratio. That is wrong. So that is decreases with cutoff ratio. So the answer is, so 1, 2 and 3. The statements 1, 2 and 3 are right. So this is also wrong. Okay. So this is also wrong. So the answer is A. The answer is A. So the next one. We can go to the next one. So consider the following statements related to the air standard Otto, diesel and Brayton cycle. So Brayton cycle has at least one isentropic and one isobaric process. Brayton cycle has one isentropic and one isobaric process. Otto cycle has at least one isentropic and one isochoric process. Otto cycle constant volume process. And diesel cycle has at least one isentropic and one isothermal process. One isothermal. So do you have isothermal process in diesel cycle? No, we don't have anything. So at least one of the cycles has an isothermal process for which of the following options. So that is, both the statements are consistent with the operations of the above cycle. So that you can see here. So Otto cycle has isochoric and reversible adiabatic. So then you can see that Otto cycle has isochoric and reversible adiabatic. So this Q is right. This Q is right, and you can see that a diesel cycle has isochoric, isobaric and adiabatic. So diesel cycle has adiabatic is there, reversible adiabatic is there, isochoric and isobaric. So this is wrong. So wherever R comes, so you will not get the answer, you will not get these answers. So R is wrong. So P is there. So in all the other cases you can see P. And Breton cycle, the next one is Breton cycle. It has isobaric and reversible adiabatic. Isobaric is there and reversible adiabatic is there. So right. Okay. So on the third statement, so at least one of the above cycles has an isothermal process. So is it right? No, this statement is wrong. This statement is wrong. Okay. So we don't have isothermal in diesel cycle. Okay, so that is also wrong. So the answers are P and Q. So S is wrong. S statement is wrong. So the answer is P and Q. So only these two statements are right. Okay, so the answer is B. So as far as we have seen this Otto cycle, diesel cycle, dual cycle, Stirling cycle and Ericsson cycle. So and also the performance of internal combustion engines. And then what are the statements that are related to all these air standard cycles, and how we can get problems, numerical statistical problems on these cycles, and also how we have seen how we can get these objective type questions in the above air standard cycles. So you should be thorough with the basic concepts, that is about its process and about its heat energy that has to be produced, and how much of work is carried out during each and every process, and you should know the number of isothermal process, number of isobaric, isochoric and adiabatic, that is reversible adiabatic or isentropic process. So you should know all these things. So only then, so because if you are going for just an fully of objective, so you may not able to answer the gate questions. So you have to read the basics and the informations which are given for this Otto cycle, diesel cycle, dual and Breton, then that is limited, that is dual combustion cycle. So you have to study the basics of all this. So then only you may able to get a clear idea about all these cycles. So simply studying the objective questions, so will not make you clear to answer the questions which are given in GATE, not only in GATE 2021, so but also in the forthcoming GATE exams also. Okay, so you have to be thorough with the basic concepts. So that is my sincere advice to the students who are going to appear for the GATE 2021 exams. Thank you.